Many Retrieval-Augmented Generation RAG systems stumble not because the language model lacks intelligence, but because the architecture is too simplistic. When faced with complex, multi-step queries, a linear, one-shot approach just can't keep up. Imagine trying to answer a question that requires reasoning, reflection, and smart decision-making like how we humans research and synthesize information. This is where agent-driven actions within the RAG pipeline become essential. In this video, we'll explore how to build an agentic, deep-thinking RAG pipeline that can handle truly complex queries, moving far beyond the limitations of basic RAG setups. A deep-thinking RAG pipeline is designed to mimic how a human researcher would approach a challenging question. It starts by breaking down the user's query into a structured, multi-step research plan. For each step, it retrieves information using adaptive strategies, refines results with high-precision re-rankers, and compresses evidence into concise context. After each step, the agent reflects and updates its research history, building a cumulative understanding. A policy agent then critiques the progress, deciding whether to continue, revise, or finish. Finally, all evidence is synthesized into a comprehensive, citable answer. This cyclical, agentic process is what sets deep-thinking RAG apart. Before diving into code, a robust environment is crucial for a production-grade AI system. This means making deliberate choices about configuration, model providers, and tracing tools. Using a central configuration dictionary allows for easy adjustments and experimentation. For example, you might select OpenAI as your LLM provider, specify powerful and fast models for different tasks, and set up tracing with tools like LangSmith for debugging and visualization. Securely managing API keys and organizing your project structure ensures that as your pipeline grows in complexity, you can maintain control and reliability. A strong RAG system needs a demanding knowledge base to showcase its capabilities. In this example, we use NVIDIA's 202310K, filing a comprehensive real-world document full of business operations, financials, and risk factors. The pipeline includes a custom function to download, parse, and clean the document, transforming raw HTML into structured text suitable for ingestion. This step ensures that the RAG pipeline works with high-quality, relevant data, setting the stage for accurate and insightful retrieval and reasoning. To truly test a deep-thinking RAG pipeline, you need queries that require multi-hop reasoning and multi-source knowledge. For instance, a query might ask for key risks from NVIDIA's 10K and then require recent news about AMD's AI chip strategy, synthesizing how AMD's moves impact NVIDIA's risks. This is challenging because it demands information from both static internal documents and dynamic external sources, as well as the ability to synthesize and analyze across contexts. Standard RAG pipelines often fail here, highlighting the need for advanced, agentic approaches. Shallow baseline RAG pipeline loads and chunks the document, creates vector embeddings, and assembles a linear retrieval chain. When tested with a complex query, it often returns irrelevant or incomplete answers. For example, it might retrieve general information about competition but miss specific, up-to-date details about AMD's 2024 strategy. The system doesn't realize it lacks crucial information and can't plan or use external tools. This demonstrates that the failure isn't due to the LLM's intelligence, but the pipeline's simplistic, linear architecture. To enable deep reasoning, the agent needs memory. This is managed through a structured RAG state, which tracks the original question, the multi-step plan, past steps, current step index, retrieved documents, re-ranked results, synthesized context, and the final answer. Each research step is represented by a step object containing the sub-question, justification, tool choice, keywords, and document section. This structured memory allows the agent to reflect, critique, and make strategic decisions, enabling iterative, context-aware reasoning. The first cognitive leap is strategic planning. Instead of treating the user's query as a single search, the agent decomposes it into a sequence of sub-questions, each mapped to the best tool internal document search or web search. The planner agent uses a structured prompt and outputs a plan object, ensuring each step is explicit, justified, and tool-aware. This approach guarantees that the agent's strategy is clear, sequential, and machine-readable, setting the foundation for effective multi-hop reasoning. Generic sub-questions aren't great search queries. The query rewriter agent transforms each sub-question into a keyword-rich, context-aware query, leveraging relevant keywords and past research context. This optimization step dramatically improves retrieval accuracy, ensuring that the search engine or vector store returns the most relevant documents. By tailoring queries to the retrieval method, the agent maximizes both recall and precision, making the entire pipeline more effective. To enable precise retrieval, each document chunk is tagged with metadata, such as its section title. This allows the agent to filter searches by section, focusing only on the most relevant parts of the document. For example, if the planner suggests looking in Item 1 Ampere, Risk Factors, the retriever can target just those chunks. This metadata-aware approach transforms the retriever from a blunt tool into a surgical instrument, dramatically improving the relevance of retrieved evidence. The heart of the Agentic RAG pipeline is a multi-stage retrieval funnel. First, a retrieval supervisor agent dynamically chooses the best search strategy vector, keyword, or hybrid based on the sub-question. The recall stage casts a wide net, while the precision stage uses a cross-encoder re-ranker to filter down to the top results. Finally, a distiller agent synthesizes the top evidence into a single, concise context. This funnel ensures that only the most relevant, high-quality information is passed to downstream reasoning agents. No matter how rich your internal knowledge base, some queries require up-to-date, external information. The agent integrates a web search tool like Tavily to fetch recent news or developments. The results are formatted into the same structure as internal documents, allowing seamless integration into the retrieval and synthesis pipeline. This augmentation gives the agent a window to the outside world, enabling it to answer questions that span both static and dynamic sources. After each research step, the agent reflects on its findings, summarizing the distilled context into a concise, factual sentence. This summary is added to the research history, building a cumulative understanding. A policy agent then reviews the entire history, the original plan, and the question, making a strategic decision. Should the agent continue, revise, or finish? This self-critique loop is what elevates the system from a scripted workflow to an autonomous reasoning agent. All these specialized agents, planner, retriever, re-ranker, distiller, reflection, and policy, are wired together as nodes in a workflow graph. Each node takes the agent's current state, performs its task, and updates the state. This modular node-based design enables flexible, iterative reasoning, allowing the agent to adapt its strategy, revisit steps, and synthesize information from multiple sources. The result is a robust, production-grade RAG pipeline capable of tackling the most challenging queries. The culmination of the Agentic RAG pipeline is the synthesis of a comprehensive, citable answer. By combining structured planning, adaptive retrieval, high-precision filtering, contextual distillation, and strategic reflection, the agent delivers answers that are not only accurate, but also deeply reasoned and well-supported. This approach transforms RAG from a simple retrieval tool into a true research assistant, capable of tackling the most demanding, multi-hop, multi-source queries in real-world scenarios.